14.3 Pressure Measurements. The outline of this video is as follows. We will begin by exploring the classic mercury barometer, a device used to measure atmospheric pressure. We will perform a calculation to see exactly how the height of the mercury column relates to the pressure exerted by the air around us. Next, we will examine a similar instrument called the open tube manometer, which is used to measure the pressure of a gas inside a container. Finally, we will define and distinguish between two important concepts: absolute pressure and gauge pressure. Understanding this difference is key to correctly interpreting pressure measurements in many practical situations. Now that we understand what pressure is, let us explore the practical question of how we actually measure it. A key concept here is barometric pressure, which is simply the current, local pressure of the atmosphere. You have likely heard this term in a weather report. This local pressure is not constant. It fluctuates with weather conditions and altitude, so it often differs from the standard atmospheric pressure we have defined as P0. To make these measurements, we rely on specific instruments. The two classic devices for this purpose are the barometer, which is designed to measure atmospheric pressure, and the manometer, which is used to measure the pressure of a gas in a closed container. These instruments provide a direct and tangible way to quantify the forces exerted by the fluids all around us. Now let us look at a classic instrument for measuring atmospheric pressure, the mercury barometer. The setup, invented by Evangelista Torricelli, is quite clever. A long glass tube, closed at one end, is filled with mercury and then inverted into a dish also containing mercury. The mercury in the tube drops slightly, creating a near-perfect vacuum in the space at the top, where the pressure is effectively zero. The key insight is that the surrounding atmosphere pushes down on the mercury in the open dish. This external atmospheric pressure is what supports the column of mercury inside the tube. The system reaches equilibrium when this atmospheric pressure, P0, is perfectly balanced by the pressure exerted by the mercury column. This fluid pressure is given by the density of mercury, rho Hg, times g, times the column's height, Ah. Therefore, the height of the mercury column is a direct measure of atmospheric pressure. Let us apply the barometer principle to a practical calculation and determine the height of a mercury column supported by one standard atmosphere of pressure. We start with our pressure equation, P0 equals rho times g times h. To find the height, we rearrange this to get h equals the pressure P0 divided by the quantity rho times g. Now we can substitute the known values. For P0, we use 1.01 3 times 10 to the power of 5 pascals. The density of mercury, rho Hg, is 13.6 times 10 to the power of 3 kilograms per cubic meter, and g is 9.80 meters per second squared. Performing this calculation gives a height of 0.760 meters, which is also 760 millimeters. This result is so fundamental that it forms the basis of a formal definition. 1 atmosphere is officially defined as the pressure exerted by a column of mercury that is exactly 0.7600 meters high at 0 degrees Celsius. This slide illustrates two classic instruments that use the height of a fluid column to measure pressure, which is a direct application of the principles we just discussed. First, on the left, is the mercury barometer. It is designed to measure absolute atmospheric pressure. An inverted tube of mercury sits in an open dish of mercury. The pressure of the atmosphere pushing down on the dish supports the weight of the mercury column in the tube. Therefore, the height of this column is a direct measure of the surrounding atmospheric pressure. Second, on the right, is the open tube manometer. This device measures the pressure of a gas inside a container relative to the atmosphere. The gas pushes on the liquid in one arm of the U tube, while the atmosphere pushes on the other. The difference in the liquid heights tells you by how much the gas pressure is greater or less than atmospheric pressure. This difference is often called the gauge pressure. In both cases, we can determine an unknown pressure simply by measuring the height of a liquid column. Now let us examine another important pressure measuring device called the open tube manometer. This instrument is used to find the pressure of a gas inside a closed container. The setup consists of a U-shaped tube containing a liquid. One side of this tube is connected to the gas vessel, while the other side is left open to the atmosphere. When the system is in equilibrium, the pressure at any 2 points at the same horizontal level within the liquid must be equal. The pressure on the gas side, which we will call P, must therefore balance the pressure on the open side. This pressure on the open side is the sum of atmospheric pressure, P0, plus the pressure from the excess column of liquid of height h. This fluid pressure is ρ times g times h. Equating the pressures on both sides gives us our key equation. P equals P0 plus ρ times g times h. This means we can determine the unknown gas pressure simply by measuring the height difference of the liquid in the tube. Let us clarify two important terms used in pressure measurements: absolute pressure and gauge pressure. Understanding the difference is crucial for interpreting real-world measurements correctly. First, absolute pressure, which we denote with A capital P, is the total or true pressure at a point. For the open tube manometer, the absolute pressure of the gas is the sum of atmospheric pressure and the pressure from the fluid column. That is, P equals P0 plus ρ times g times h. In contrast, gauge pressure is the pressure measured relative to the local atmospheric pressure. It is defined as the difference between the absolute pressure and atmospheric pressure. For the manometer, the gauge pressure is simply the contribution from the fluid column, the quantity ρ times g times h. A perfect example is the pressure in your bicycle tire. A tire gauge measures the pressure of the air inside the tire times the atmospheric pressure outside. Therefore, it measures gauge pressure. The essential distinction is that absolute pressure is the total pressure, while gauge pressure is the excess pressure above atmospheric pressure. This quiz tests our understanding of how a barometer's design depends on the fluid it uses. We need to figure out which of the listed fluids would create the tallest columns. Let us recall the principle of a barometer. The pressure exerted by the fluid column must balance the atmospheric pressure. This is described by the equation: atmospheric pressure equals the fluid density, ρ times g times the column height, h. If we solve for the height, we find that h is equal to the atmospheric pressure divided by the quantity ρ times g. This equation shows that the height of the column is inversely proportional to the density of the fluid. In other words, as the fluid's density goes down, the height of the column needed to balance the atmosphere must go up. To answer the question, you would need to compare the densities of the four options. The fluid with the lowest density will be the one that produces the highest column. This is precisely why dense mercury is often used in practical barometers. It allows the instrument to be a reasonable size. Let us summarize the key ideas we have just covered about measuring pressure. First, we saw that a barometer measures atmospheric pressure by balancing it against a column of fluid, like mercury. The atmospheric pressure, P0, is calculated as the fluid's density ρ times g times the column's height h. Second, we looked at the open tube manometer, which measures the pressure of a contained gas, P, relative to the atmosphere. Here, the absolute pressure of the gas is equal to the atmospheric pressure plus the quantity ρgh. This leads to our final key distinction: absolute versus gauge pressure. Absolute pressure is the total, true pressure. Gauge pressure is the excess pressure above atmospheric pressure, calculated as P minus P0. For instance, the reading on a tire pressure gauge is a gauge pressure. The main takeaway is that we can measure pressure either in absolute terms or relative to the atmosphere. To wrap up our discussion, here are 2 review questions to help you check your understanding of pressure measurements. The first question explores why we use a very dense fluid like mercury in barometers. It asks you to calculate what the height of a barometer column would be if we used water instead. Recall that atmospheric pressure is balanced by the pressure of the fluid column, which is the density times G times H. Since water's density is much lower than mercury's, you will find the resulting height is impractically large. The second question is a practical problem involving an open-tube manometer. You are asked to find the absolute pressure of a gas, given the height difference in the 2 arms of the U tube. The key here is to use the manometer equation, which relates the gas pressure, atmospheric pressure, and the pressure due to the fluid column. Remember to convert the height from centimeters to meters before you calculate the final answer in pascals. Please pause the video and work through these problems to solidify these concepts.